Hi, and welcome back to the NeuroBytes video experiment series. Have you ever wondered why, when you go to the doctor's office, he or she taps your knee with a hammer during a physical exam, and why your leg jerks in response? How does that happen? Today, you're going to learn about the circuit in your body that produces that reflex while building a neural circuit of your own. To do this, you will need a touch sensory neuron, interneuron, and 2 motor neurons. You'll also be using the model leg in your kit, which may look a bit different from this one, so take that out now if you haven't already. Your real leg has 2 main muscle groups that are activated when your patellar tendon, or knee jerk, reflex is activated. The quadriceps on top of your leg, and the hamstrings on the bottom of your leg. Your NeuroBytes kit doesn't use real muscles, but it can produce motion. Real motor neurons cause muscles to contract when they fire action potentials. Action potentials in your NeuroBytes motor neurons also cause your kit motors to move, and that's what you'll be using now. If the 2 motors simulating the quadriceps and hamstring muscles are not already attached to your leg model, attach them now. Then, attach the touch sensory neuron to the leg model. A tap on the knee switch will eventually start the reflex, just like a tap on your real knee does. Reflexes happen so fast that the brain doesn't really get involved. The spinal cord does all of the processing. So, you'll need to build a spinal cord with neurons to process that knee tap. Take the spinal cord cutout out of your kit and attach an interneuron and 2 motor neurons as shown here. If you remember back from the reflex diagram, the interneuron in the circuit releases inhibitory neurotransmitters onto the hamstring's motor neuron, so connect an inhibitory neurotransmitter cable between these 2 NeuroBytes in your spinal cord model. Next, connect the hamstring servomotor cable to one of the outputs on this hamstring motor neuron. Then, connect the quadriceps servomotor cable to one of the outputs on the quadriceps motor neuron. You just built the output from the spinal cord, now you need to provide the input. Connect 2 excitatory neurotransmitter cables to the output of the touch sensory neuron. One of these will then be connected to a short dendrite on the spinal cord interneuron, while the other will be connected to any of the dendrite inputs on the quadriceps motor neuron. Remember from before that all of the inputs on the motor neurons are the same. Finally, power up your circuit by connecting your battery pack and black power cable to any of the neurons in your circuit. After ensuring your neural circuit connections look like this, give your touch sensory neuron switch a click. What you should see is that your model leg kicks, just like your real leg does at the doctor's office. That kick is in response to the knee tap, and you should be able to follow the neural signal that gets sent around the spinal cord network you built. First, there is an action potential in the touch sensory neuron, which next causes the interneuron and the quadriceps motor neuron to each fire action potentials. As the quadriceps motor starts to extend the leg, the hamstring's motor neuron is inhibited by the interneuron, which then results in the hamstring motor rotating in the same clockwise direction, or stretching the hamstring muscle. As you've probably noticed, this hamstring stretching does not happen at the exact same time as the quadriceps contraction. In the real nervous system, it does not either. The delay you saw in your NeuroBytes activated motor movement is hundreds of times shorter in your real nervous system because real nerve impulses move much faster than they do in your neuron simulators. In fact, action potentials in real neurons can move as fast as 200 miles per hour. We've slowed it down in your NeuroBytes neuron simulators so you can better understand from and experiment with your new artificial nervous system.